Hello students, welcome to our channel. I know it's been a long break since we have posted any video because I was not available. So it's a bit, the temperature has fallen, it's a bit cold here. So why do we feel cold? That's another thing, okay. When thermodynamics will come, we will study that. So let's now continue to our chapter. We are studying about capacitance. Okay, we are studying about capacitance. So we shall be continuing from that. So we had learnt about the capacitance of a parallel plate capacitor system with dielectrics inside them, and we had already done those cases of introducing more than one dielectric inside those parallel plates. Okay, so today let's be serious. So from today now we shall be continuing capacitance. Okay, so let me see. It is, yes, it is recording. So let us learn about capacitance. So today we shall be learning about the energy stored in a capacitor. Okay, the energy stored in a capacitor, it's a very small concept. Energy stored in a capacitor, make it a heading. Energy stored in a capacitor, it is a very small mathematical concept, but the formula is very important and it might come in the exams. So the formula is very simple. The concept will not be asked in the exams. The formula will be asked, or a problem will be asked on the basis of that formula. Okay, so that it is same formula, but it can be modified into two or more formulas by just replacing q is equal to this or that, this or that. Okay, so let's just focus on that. So first listen to me. So we charge a capacitor. Okay, we charge a capacitor. That means we have learned earlier that if you add charges to a system, the potential of that system increases. Okay, so if you add positive charge, let it be positive charge. If you add positive charge to a system, its potential increases. Okay, so if it is a system, you are adding some charge, the potential of the system increases, and now you have to add more charges to it. You have to add more charges to it. That means you have to do some work against this potential. You have to do some work against this potential. To add even more charges, you need to do some more of the work to overcome this potential in this object. Okay, so similarly, the thing is that what is the energy stored in a capacitor? The definition is the work done. You can try out the definition. The work done to charge a capacitor is the energy of the capacitor. Energy of the capacitor. It is the definition of the energy stored in a capacitor. That how much is the work done to overcome that potential. So whenever you are adding more and more charges, you have to do, or you are increasing that potential by this much. Okay, you are adding a charge small q, you are increasing that potential to small v. Okay, so if it is an object, you are adding a charge q to it, that means you are raising the potential of the object by a small amount v. You are adding charge q and increasing the potential of that object by, or a parallel plate capacitor or a capacitor, by a potential v. Okay, so let the final charge be q and the final potential be v. Okay, these are small things and these are big things. So if you add a small charge q, you are increasing the potential of that capacitor by a small potential, that is called v, and finally you have added this much of charge, and finally the potential of this object is capital V. So let us try to do that mathematically. So when you add, as we know, if q is added, then work done or v is equal to w by q. It is equal to w by q. Okay, this is the main formula as you have learned from the potential chapter. This is the main formula here. Okay, if the potential of the capacitor is increased to V by adding charge small q to it, small q to it, then you can write this formula. Then V is equal to W by U. Then the work done, let the work done be, then the work done be. Please continue from this point. Work done be dW. Okay, this is the small amount of work done. So what would be dW? It's dW is equal to V dQ. You are adding a small amount of charge. You are adding a small amount of charge. So let me just replace this pen or add some ink to it so that it runs smooth. So in order to just find the total work done, you have to integrate it. Okay, in order to find the total work done, in order to find the total work, we integrate it. Okay, we integrate it dW from 0 to W. V can be taken out, dQ. Not B, we just don't take it out right now. Integration over V dQ. Our variable is Q, so it is from 0 to Q. Okay. Now, as we know, V is equal to W by Q. That means W by Q. It is W by Q. So, we can actually work on that formula to find out the integration. The problem in this thing is that we have to add something bit different to it, or we cannot continue the integration. Okay, if V is the it is the amount of work done to shift that charge from infinity point to a certain point, we have to just determine another thing, that is capacitance. We have to determine another thing, that is capacitance. As we know, capacitance C, capital C, is equal to Q by V. That means V is equal to Q by C. Okay, V is equal to Q upon C. We have to introduce a constant factor C, that is the capacitance of the system. So just try to replace V by Q by C. Q by C is equal to, no, sorry, the C will get out only. The C will get out only is Q dQ. Okay. Now you have to confirm the integration of this point. So is this recording or not? Yes, it is recording. So Q dQ, it is Q square upon 2. The limits are 0 and Q. So let me take it down to a little bit lower place. So what is W? W is equal to 1 upon C Q square upon 2. Sorry, excuse me. So just you have seen the formula and how it is derived. So I can remove this portion. So here W is equal to 1 by C Q square by 2 or Q square upon 2C. It is your important formula. Okay. So this formula now can be modified into different things. Like if you are given charge and potential, you can also find out the energy of the energy stored in that capacitor. If you are given only C and Q and any other things. Okay. So let the potential be V when Q charge is given to that capacitor. So V is equal to Q by C. Okay. So what is Q? Q is CV. Okay. So in place of Q, just write CV, that is all squared, to C. Or you can actually write it like this, CV squared. So work done is also is equal to half CV square. So it is equal to Q square by 2C or half CV square. So either of these three things Q, C and V. If any of these two things are given to you, you can actually calculate the energy of that capacitor. Okay, so no need to worry. If C is not given, then Q and V will be given. If V is not given, then Q and C will be given. And if Q is not given, C and V will be given to you. So no need to worry. So this is the energy stored in a capacitor. This is the energy stored in a capacitor. So you can write this formula. It is an important formula. Let me write it a bit better. Upc V square and Q square by 2C. So W is equal to half C V square is equal to Q square by 2C. This is the amount of work done, your required answer. So if the question asks you that find the energy stored in that capacitor, you can either approach the question by this method or by this method, whichever things or whichever quantities are available to you. Okay. So now we shall be learning about network of capacitor, how we can connect more than one capacitors. Okay. As we have learned in our previous classes, like in our 10th class, we learned about the equivalent resistance of a given group of resistors. Okay, if a given number of resistances are connected by series connection or parallel connection or mixed connection, we had to find the equivalent resistance of that circuit. In this thing, we shall also try to learn about the equivalent capacitance of a given capacitance system, okay, which consists of multiple capacitors. So let us first try to this is name it be one. So parallel. So let me write equivalent capacitance of a parallel. Equivalent capacitance of a parallel connection of capacitors. So you are given capacitors, a parallel connection of capacitor. What is a parallel connection of capacitor? That means, so let me build it and I will try to explain it later. Multiple capacitors. The numerous capacitors, okay. This is the battery. If you name this capacitor C1, it is C2, it is C3, and at last draw another capacitor, name it Cn. Cn, okay. Okay, this capacitor is Cn. The battery is V. So what is a parallel connection? The parallel connection says that one of the plates are connected to a point or to a common point and the other plate of the individual capacitors are connected to another common point, and that type of connection is called parallel connection of capacitors. So you can actually see the plates or the capacitors are connected parallelly. Okay, there are n capacitors. So they are drawing a charge Q from the battery. They are drawing a charge Q from the battery. The total amount of charge they are drawing from the battery is Q. Okay. So, for instance, let it draws, that means Q here is getting divided. Q here is getting divided into these branches. Okay, Q here is getting divided into these branches. That means the charge that is reaching C1 is Q1, the charge that is reaching C2 is Q2, the charge that is reaching Q3 is Q or C3 is Q3, and the charge reaching Cn is Qn. Okay, so they constitute the total charge Q. Okay, the Q is divided into Q1, Q2, Q3 and the number of capacitors. So we can also determine the amount of charges in those capacitor system. Okay, so since you can see that it is a parallel system, that means the potential difference between those two plates in every capacitor is same. That means the potential difference between or for C1 is V, for C2 is V, for C3 is V, for Cn is also V. Okay, so we are going to write some notes about it. Let me just see if it is continuing or not. So let us write some notes from it. So in order to write some notes, previously you have to add something to the note. That is, you are finding that equivalent capacitance of this system. That means find such a capacitor that it behaves like the equivalent of C1, C2, C3 and dot 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 Cn. Okay. So here we are going to find a single capacitor whose capacitance C is behaves equivalent as C1, C2, C3, Cn behave. Okay. So whatever their behavior is, the single capacitor will collectively behave like the equivalent of these individual capacitors. Okay. So we are going to find that thing. So it is a parallel plate capacitor system. So the first plates are connected to a common point and the second plates are connected to another common point in a parallel. You can add this thing in a parallel connection. The first plates are connected together to a common point. That common point in this figure is A. Okay, common point A that is in this figure, and the second plates of all the capacitors. The second plates of all the capacitors are connected to another common point. Are connected to another common point, and in this figure it is B. Common point B. Let me replace it. It is still showing some problem. Okay. Let me refill it again. I don't know. I think it is the winter season. You have to refill these pens with this ink, this special ink. Okay. You have to refill it like this. So that it runs smoothly and the ink that comes out is black. Okay. You can actually see it is drying out. From the last sentences, from the last two sentences, you can actually observe that it is drying out. It's due to this winter season. So no problem in that. We can refill it as many times as we want. So let see the change C1, C2. Okay, I have written it. Okay, you don't need it now. So what will be our equivalent diagram? It will be like this. Our equivalent diagram will be like this. Okay, this is V, this is C. Okay, so this is drawing a charge Q, and so you can write from here C1 is drawing Q1, C2 is drawing, it is still making noises, examining my pixels. Okay, so we need not worry. So C1 is drawing the total charge drawn from the battery, the total charge drawn from the battery is Q. That means you can add here, that means Q is equal to Q1 plus Q2 plus Q3 plus like this. Okay. So now the potential difference between the two plates of capacitor C1, you can actually write it here. The potential or another sentence you can add, that is, since it is a parallel connection, you can add it here. Since you have to add these things systematically in your note copy. Okay, since I have no more space left, so I am writing it like this. Since it is a parallel connection, so potential difference across every capacitor is V. Capacitor is V. That is equal to the potential of the battery. That is equal to the battery. Okay. You can actually write the two plates of the battery. We need not write that if you can understand. Okay. So if you consider every capacitance system, so C1, so for the first capacitor C1 equal to Q1 by V. C1 equal to Q1 by V. Similarly, for the second capacitor, it's C2 equal to Q2 by V. Okay, so for every capacitor you can write it like this. The numerator may be different, but the denominators are same, because every capacitor is connected to is parallelly connected to the same potential difference. So from this equation you can actually write Q1 equal to C1V. Similarly, from this equation you can write Q2 equal to C2V. Okay, you can write it like this, Q2 equal to C2V. Now I have to remove this part so that we can continue. I hope that you have written all these things. So let us continue from this point. I really need this. With your prior permission, I have removed it. So don't blame me later. So as Q1 equal to C1V, not V1, okay, it is V. Q2 equal to C2V. And similarly, we can write Q1 equal to CNV. Okay, now we know that if it acts as in equivalent capacitance, let the equivalent capacitance be C, then that by that same thing Q is equal to CV, and Q is equal to CV. So now Q is equal to Q1 plus Q2 plus Q3 plus dot dot dot. You have to extend it like this. Okay, so now replace these things. CV, C1V plus C2V plus dot dot dot. So you can actually see I have replaced these things with these things. So CV plus C2, if you take V as common thing, you will see it like this. And actually the equivalent capacitance C, V from both sides get cancelled out. It is equal to the sum of the individual capacitors. If you are given a parallel connection of different capacitors and you have been asked to find out the equivalent capacitance of that system of parallel connection, so simply you can add the individual capacitances of the given system and you can find the equivalent capacitance of that system. So if you have been asked to find out the parallels or the equivalent capacitance of the system, you need to add C1 with C2 with C3 and so any number of capacitor present in the system, you have to add them. Okay, so this is our main formula. So let me write it like this. I hope that you have written this thing. So let me replace this thing with the formula required. So the required formula, you can write C or CEQ. It will be C1 plus C2 plus C3 and plus dot dot dot. This is your required formula. And in our statements, you can write it like this: in a parallel connection of capacitor, in a parallel grouping, of capacitors, the equivalent capacitance is equal to the sum of individual capacitances. So if you are given C1, C2, C3 and anything like that, like 5 capacitors having capacitance C1, C2, individual capacitances C1, C2, C3, C4 and C5, and you have been asked to find out the equivalent capacitance of that network, so you have to simply add it. So I think you are a little bit confused, since in network of resistors, in grouping of resistors, you learned that it is like a series connection. Okay, it is like a series connection. It is the formula for a series connection. If you are asked to find out the equivalent resistance of resistance R1, R2, R3, so you had to add them when they are connected in series. Like R1 equivalent resistance R is equal to R1 plus R2 plus R3 plus R4 and dot dot dot. This is the series connection formula. But you are, how teacher, you are giving us the formula for parallel plate capacitance systems, but it is like that only. I have showed you the formula. I have showed you the mathematical formulation. So it is a bit different. It is a reverse case. Okay. So if you remember one thing, that is the equivalent resistance, so you can actually calculate the capacitance, because if you remember the series formula for resistance, it is the or series formula and the parallel formula for in case of resistance, it is the reverse case in place of or in case of capacitance. Okay, so I think parallel connection of capacitors is over. Now we shall be trying to find out the equivalent capacitance in a series connection of capacitors. So let us see. At last you can add a thing like this. Okay, you can add a thing like this. You need not write it like this if you know this. This is the symbol for summation. Okay. So we shall be continuing for equivalent capacitance of a series connection of capacitors. Okay. Series connection of capacitors. I hope you are enjoying this thing because I am enjoying. And I can only hope you are enjoying or not. You are enjoying or not, you can let me know in the comments. So this is our second thing. So you have to write it a whole. I have just to remove this thing. So our second thing is an equivalent capacitance of a series connection of capacitor. So see how it is simple for me to just replace the parallel thing with the series thing. It is a bit easy for me. Okay, it was always easy for me. So equivalent capacitance of a series connection of capacitor. That means you have to draw the system. This is C1, this is C2, this is C3, dot 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 dot. This is C and they're connected to a single battery of potential difference V. Okay, this is V, this is C1, this is C2, this is C3, dot dot dot, Cn. So an end-to-end connection is called a series connection. That means the end of this capacitor is connected to the start of this capacitor. Similarly, the end of capacitor C2 is connected to the start of capacitor C3. This is called series connection. So you can write something about the series connection. It is an end-to-end connection of capacitors. It is an end-to-end connection of capacitors. Capacitors C1, C2, C3 and many capacitors. Okay. So they are, every capacitor is drawing a charge Q from the battery. Okay. So the charge here, the first plate is connected, as it is connected to the positive plate, it is Q and it is minus Q. It is Q and it is minus Q. It is Q and it is minus Q. Similarly, it is Q, it is minus Q. But the potential difference of between the plates of C1 is V1, it is V2, it is V3, it is Vn. Okay. So we have to write something, that is, we have written that it is an end-to-end connection across C1. Across C1, potential difference is V1. Difference is V1 and charge is, and it is charged, so you can write it like this, and it is charged to Q, to an amount Q. Okay. Similarly, all the capacitors, have their individual potential differences, but all of them are charged to Q. All of them are charged to Q. Okay. So in this connection, we have to write V. So if it is acting like a capacitor that we have similarly as all of these capacitors we have collectively, then we have to draw it like this. It is V, it is CEQ, the potential difference is V. Okay. So it is drawing charge Q, it is minus Q. Now, C1 equal to Q by B1. That means B1 is equal to QC1. Formula for capacitor 1. Similarly, B2 equal to QC2, B3 equal to QC3, and it will go on like this. And similarly, B, the bigger potential difference, is equal to QC or QCEQ. In a series connection, the individual potential differences add up to the collective potential difference of the battery. So, V1 plus V2 plus V3 will give you V. As you know the formula for this individual potential difference, you have to replace these things with those things. That is, V1 is replaced with QC1 plus V2 is replaced with QC2 plus V3 is replaced with QC3 plus dot dot dot, and V is replaced with QCEQ. Okay, so in the left hand side you can actually see that Q is common to every term, so we can take it as common. That is C1 plus C2, or I am doing wrong. No, I am doing wrong. I am doing wrong. I am doing wrong. I have done wrong from this formula onwards. Okay, so no need to. So V1 equal to Q by C1. Okay, so I apologize for that mistake. I went into the flow. So V1, so V2 is also equal to Q by C2, and V3 is equal to Q by C3, and similarly V is equal to Q by CEQ. That is the equivalent capacitance. So in a series combination, you have to add the individual potential differences to find out the common or the collective potential difference. Okay. So V1 plus V2 plus V3, that is the potential difference across individual capacitor, they collectively form V. So continue from this side. V1 can be replaced by Q by C1. Q by C1 plus Q by C2 plus Q by C3, and it is Q by CEQ. So you can see in the left hand side Q is common to every term, so we can take it common, that is Q is common, that is given 1 by C1 plus 1 by C2 plus 1 by C3 plus dot dot dot, Q is equal to Q by CEQ. So if some spot remains, so I have to take it down a bit. So from this thing, you can actually see that 1 by CEQ, as Q and Q cancel from both sides, it is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and it is like this. Okay. So to find 1 by CQ for the equivalent capacitance of the system, you are summing the reciprocal of each capacitance. This is the required formula. So in order to find out the reciprocal of that equivalent capacitance, you have to add the reciprocal of individual capacitances and sum them. The sum which you will be finding, it is equal to the reciprocal of the equivalent capacitance. So if you find 1 by Cn is equal to 5, then equivalent resistance is equal to 1 by 5. You have to find its reciprocal, then it is equal to 0.2. Okay, this is how it works. So let me just frame a sentence for you so that you can actually understand this. So I have to frame a sentence to that side of that solution. So it is the required formula. So what does the statement will say? The reciprocal of the equivalent capacitance equivalent capacitance is equal to the sum of the reciprocal of the individual capacitances. So if you were given capacitance C1, C2, C3, this is the statement form. If you are given capacitance C1, C2 and C3, so how do you find, what is the method to find capacitance C or equivalent capacitance? So I hope that you have written all of these things. So I am taking the camera to the top a bit. So I hope that you have written all of these things. So I am removing it, give you a better understanding of this formula. So you are given a parallel connection of, a series connection of C1, C2, C3. These three connections are given to you. So you need to find out the equivalent capacitance of this network of capacitors. Okay. So in order to find its capacitance, we do it like this. It's equal to 1 by C1 plus 1 by C2 plus 1 by C3. You do the mathematical formulation like adding these things. So how are we going to add these things? That is C1, C2, C3, C2, C3 plus C1, C3 plus C1, C2. Okay, so what is C equivalent? You have to reverse it or reciprocal it. C1, C2, C3 divided by C2, C3 plus C1, C3 plus C1, C2. You can do it like this. So today's class was this much. So in the next class we shall be continuing with some problems from the grouping of capacitors that will be concerned about the parallel connection of capacitors and series connection of capacitors. Up until then, take care. Exams are coming, so, and try to do some problems so that you can know the approach of solving a problem, a numerical. So up until then, take care. So watch our videos, share it among your friends. If you just give a like, subscribe to our channel. Thank you.